Welcome back to the course on wheeled mobile robot. This is lecture 6. You know lecture 5 we were talking about kinematic simulation of a mobile robot. In specific the land based mobile robot kinematics we have taken and we have tried to simulate it with the help of Euler method. So this particular lecture 6 we are going to talk about motion animation. So why this is motion animation required with the help of the previous code and then how we will do the motion animation, that is what we are going to cover in this particular lecture. So in that sense you can see that, so I put two things. So the motion animation is the core for this particular lecture 6. So for understanding this I am just giving a very light way. So we have used the Euler method in this form. So based on that what we know, the position propagation model is available. So based on the position propagation model we have used the already known differential kinematic model. So we have actually like derived it. So what we did, this is the code we did it in the last class. So lecture 5 if you refer, so this simulation we have taken. So now I am actually like showing it here. So this is the plot which we have done in the last class where we have taken x, y and psi. So this particular plot is actually like giving little more information, but what we wanted is slightly a different way. So when I want to see the simulation result, if it gives in the exact vehicle orientation and vehicle motion, that would be more beneficial. For example, so I am showing that the condition I have changed where the initial condition of that previous code in lecture 5 what I covered. So I put the initial conditions all are 0, but I am giving the input instead of a constant input, I am actually like giving something slightly varied where u is 0.3 and there is a rotational angular velocity which is r as given as 0.2 radian per second. So now the simulation is giving this particular result where x is actually like slightly getting bent, but we do not know what the nature, and y also like getting curved, it is like a parabola, and r is giving the psi, in the sense psi would be gradually increasing. These all actually like getting, but you see this code and this result is not giving any fruitful information. Now then one can ask, can I actually like plot x versus y? Yes, you can do, but still I am not getting the picture of what the psi is happening. So how the vehicle is actually like orient or whether the vehicle is actually like rotating about itself, these all not informatively given here, right? So then what one can see, if I incorporate one of the block which I call as a vehicle, you know like vehicle we started with a small you call blue color block, right? The similar way I am trying to incorporate in animation as a green color block. So now this block can be actually like fit it into the xy plane and I can show as a, you can say image overlap, I can show it as an animation, right? So this is what usually we are doing it. So now you can record it as a video. Now how we can do this? So for that what one can know, so the vehicle frame you know, which is we call B, the point B, that would be having a frame of xb and yb. Now if I want to know this particular coordinate, I already have it, right? So you see already this xy is there, but what I wanted this vehicle moving on this xy plane with the orientation. So in that sense what one should know, so one should know that the coordinates of this point, so I am taking as a general where the B point, which is actually like the body frame, I assume as the origin. So now in that sense if the vehicle length I call L and the vehicle width I call W, I can actually like bring the coordinates of these four corners in this form, okay. So this is actually like very simple, right? So now if I know this, what additionally I can brought, so now if I actually like put x is actually like added in everywhere in the x coordinate, what I will give, the vehicle will actually like move in x. If I put y of the value which I obtained in the previous animation or you can say simulation code, that would be added with all the y coordinate, that would be taking the y addition, right? But what one supposed to know, the vehicle is orient also, right? So in that sense one supposed to understand, if you take a random point of x1 and y1 with the help of 0, 0, so now you can see that this particular point I can draw a line. So now this point is actually like you can say associated with the frame which is xb and yb. Now this frame itself is rotating, in the sense the point x1 and y1 is part of this body, that body is rotated. How that can be visualized? I can visualize with the small, you can say picture here. You can see that now the frame B is rotated about z axis as a psi angle. So now what would be the xb? Xb become xb dash and yb become yb dash. Now what happened to the point? The point x1 and y1 also part of this body, right? So now that is also rotated. So that is what happened. Now if you look at this, so what happened? This x1 and y1 with the respect to B frame is not changed. But with respect to the original frame, which we call initial frame, it is getting changed, right? So how that can be realized? So you can actually like projection you can use. So based on the projection, what you can write? So along with you call x1 direction, which is actually like x1 dash direction, which is I am assuming that that is parallel to xb original. So what I can write? So that would be projected as x1 cos psi minus y1 sin psi. So how that can be done? You project this point. So what it would give? It would actually like give two component, right? So based on that component, you can actually like get x1 dash and y1 dash. So now these are the coordinates which is actually like modified based on the psi angle. Now how I can actually like rewrite this in a simplest form? So one easiest way, you see left hand side I can keep it as x1 dash and y1 dash as a vector. So the right hand side I can take one matrix and multiply with x1 and y1. So in the sense what one can see, it is a simple transformation matrix. So this transformation matrix, if I know, I can actually like easily portray all the points and I can actually like start do the animation. So for that what we can actually like see, we are trying to do this incorporation in the MATLAB code. So this is what we are actually like trying to do. For animation purpose, I am bringing the vehicle dimension. The vehicle length is actually like 0.6 meter and the width is actually like 0.4 meter. So now you can see that the mobile robot coordinate I can bring as mr underscore co, which is nothing but the mobile coordinates. So which is I have written as what we did in the earlier slide, probably slide number 10 or something. So you can refer it. So now this coordinate is incorporated, what one can see. So this is actually like where your x coordinate and y coordinate and the psi angle is actually like getting changed. The array would be length of t, right? So now that if I know, I can actually like put in a for loop where I can actually like run the loop from 1 to length of t, where I can say that this is animation start. If I know the psi is nothing but the third, you can say entity of the eta vector, which is I am writing psi as eta of 3 comma 1, or in the sense it is ith instant. So now I brought the, you call the transformation matrix, which I obtained in the you call slide number 13, where the rotation matrix I incorporated, that matrix I brought in. So now what I know, already the mobile robot coordinate I know, which is not rotated, but now I brought that into rotation matrix. Now what happened? The vehicle position is actually like rotated. Now this vehicle position added with, you can say x coordinate added with x value, which is nothing but eta of first component, and the y component, which is v position of 2, which I added with the second component, which is eta of second component, which is 2 comma I. So now what it will give? It will give a fill on the plot as a green patch. So that green patch would be actually like try to show. Now I want to show the profile or the path of the vehicle. So I am plotting the eta of 1 comma eta of 2, which is actually like I am plotting as up to ith instant. So now you can see this in the MATLAB code. So for that I am actually like moving into a MATLAB. So you can see that these are the things which we did in the lecture 5. So now what we added, so these are the content we have added. So where L, W I have added as length of the mobile robot and width of the mobile robot, and then I have added the mobile robot coordinate in this form. So I said I want to actually like animate. So in the sense I will be plotting sequence of image overlap one to another with passing the time, right? So in the sense I am actually like holding every image for a few seconds or few milliseconds, then I will be overlap one image to another image. So for that what I am trying to do, first I am rotating the original, you can say mobile robot coordinate with the help of rotation matrix. Then I am actually like filling as a patch. So this is a simple MATLAB command where this is actually like x position and this is y position and this is the color. So G means green. So now what I am trying to do, I am actually like trying to show this. So for that what I am trying to show is, see, I put a pass. So pass 0.1 means I am passing every segment as 100 millisecond. I am holding off, why? Because every image need not to be superimposed with the previous image. So in the sense hold on is required for initial, but hold off is required for making an animation as a moving. So if I run this code, you can easily realize what going to happen. So you can see here. So I hope you are able to see in few seconds. It takes time. We'll see. Yeah. So now you can actually like able to see. Yeah. So you can see like this. So the vehicle which is actually like look like a green patch. So that is actually like moving, right? So this is what we call vehicle animation. Now you can see that based on the orientation of the vehicle, it is moving. On top of that, the vehicle frame also looking, you can see coordinate as B, right? That B frame is the point where the blue line is actually like ending. So in the sense you can see that where the vehicle coordinate all about and how the vehicle is oriented. So these all actually like you can see in a single, you can say picture, which is actually like nothing but as an animation here. So now you compare to the previous result, although you plotted xy plane or you plotted individual coordinate, it is not giving this, you can say, fruitful information, right? So that is what one should know. So how to present the result in a betterment. So that's why this vehicle animation is important, in the sense the motion animation is important. Now once you know this, so the next lecture, what you call lecture 7, where you are bringing the, you can say, wheel kinematic model, then you can actually like put the wheel here and you can see the overall animation. So how individual wheel would be contributing, you can easily realize. For example, you have a differential wheel drive. So when you have a left drive and right drive, how it is dominating, that you can see in the vehicle, you can say motion animation, rather than just plotting time versus x of t, y of t, or time versus u and v. That is not going to helpful, but this motion animation would be very much helpful. I hope you got it how to do vehicle motion animation. So with that, I am ending this particular lecture. So far what we have seen is actually like forward kinematic model along with the motion simulation. So now we will actually like see how this would be helpful if we do a inverse differential kinematic model taken place. In the sense the eta desired and eta desired dot is given. So how one can actually like simulate this particular system and how that would be different from the general controlling. Because when I was defining what is forward and different, you can say inverse differential kinematics, I said that forward differential kinematics is equivalent to a simulating that we have done. The inverse differential kinematic, what we said as a controlling, but this is open loop control, I already mentioned. So now we will actually like move to the MATLAB, you can say code what we have done so far. So with that we will actually like change how that can be vary. For example, now I said that the eta is given, but what we have taken the inputs UVR is straight away we have given as a user command. But now this user command would go away. What that means, this input would be defined based on the, you call eta desired and eta desired dot. So for that what we supposed to know, I will actually like add a new thing which is I call desired parameter. Okay. So that too, like I will say desired states, so which I call generalized. Okay. So generalized coordinates. So these are the things which we are going to give. So obviously what you need to know, the eta desired, which I am putting as eta underscore d, that would be a vector, but it can be a, you call simple, you call constant vector. But right now I am thinking of putting it as a, you can say time varying. So I am better, I will put it this into a for loop itself, because I have already time inside. So instead of this, what I am actually like trying to put it, so that desired thing. So in the sense desired state is coming here. So this would be as a time varying input. So where I am assuming that this is actually like taking 2 cos, you can say 0.1 times of Ti, where ith instant of time we would be using. And similarly the other one I am actually like probably I am taking it as 2 minus, so that it would be easy for my further run. Okay. So the other one is actually like I am saying 2 sine of, so 0.1 times T of I. So why I have taken minus 2 minus of 2, otherwise what happened, my starting point which is actually like 0 in x axis, but in this case if I put t equal to 0, it suddenly starts from 2. So in order to make it neutral, so 2 minus of 2, so then you may ask 2 cos of this minus of 2 also will work. Yes, that will work, but you know, like the eta desired dot would be derivative of this. You know, the cos derivative would be actually like minus sign. So, if I include the minus sign here, that would be easy for further run. That is what the whole idea. The vehicle would have a forward velocity rather than reverse velocity. That is what the whole idea behind bringing the, you call 2 minus of 2. Okay. So, now I assume that this would be simply 0.1 times of t. Okay. So, now what you have derived? So, you gave eta desired, which is nothing but this is x desired, this is y desired, and this is psi desired. So, now based on that, what one can actually like find x desired dot, y desired dot, all we can actually like find. So, that I am putting as eta desired dot, I am writing as eta underscore d, that is desired, underscore dot, it says that it is time derivative. So, if I take the time derivative, this would be 2 into 0.1 into sine of, so 0.1 times of t, right. So, then it would be again 2 into 0.1 times of, so cos, so 0.1 times of ti. You see, I did not change anything, I am using the same code, only thing I am adding, instead of giving a user input directly, I am putting in a other way around. Okay. So, now if I take time differentiation of this, this would be 0.1, right. So, these are the desired, you can say, state vectors, and these are the desired state derivatives. Now, what we are actually like interested? We are interested to find what you call zeta. So, that is what you are actually like interested. So, here actually like substituting into eta dot may be like redundant, but we are actually like doing it right perspective. So, what we are trying to see, the zeta you can say of I am calculating based on what we know like j psi inverse, right. So, the j sin inverse I can write in a MATLAB, you know like MATLAB command, it is just INV. So, inverse of this. So, now what you need to have? So, here actually like eta desired dot, so that here desired, so I am actually like putting that here. Okay. So, now you can see that what we have done. So, we have taken desired state variable and that time derivative I have taken, now I am taking it this. So, this is what you call, so, so it is actually like vector of, so vector of, you can say, velocity input commands. So, that you have actually like calculated, right. So, now if I run this, what we have given, so the profile which is look like a circle, so that circle supposed to be followed. We will actually like cross check whether that is actually like done or not. So, we will just run whether there is a error free. So, I will see that is actually like error free. So, you can see like now it is actually started from 0 point and it is actually trying to make a circle. So, you can see here. So, now you can actually like see that it is started from 0 0, that is what we have intended. So, your desired and actual both are starting from 0 and it is actually like making a circle, but one can actually like see that this is actually like not completing it. So, why it is not completing? Because we have not given the psi desired dot as per the what you call the circle. So, we have actually like given in a other way around. Here actually like how the psi desired supposed to be, it would be actually like a, you can say, minus of this. Why it is so? Because it is actually like rotating in the other direction. So, that is what we have to actually like see, in the sense if I actually change minus 0.1 times of ti, then you can see that that will actually like align with this, but that is nevertheless, that is not important. What important is actually like what you have given as a user input that we are trying to follow. So, for that what we are actually like seeing that this is actually like kind of control loop, but this is an open loop. Still I am just checking. So, what would be the eta desired and what is your eta, okay, of that ith instant. Okay. So, now I am actually like assuming that this is a error. So, this error which would be having a vector. So, I am assuming that that would be having propagated. So, now I can see whether the error is exist or not. Okay. So, now if I run, so I will actually like add a plot. So, at the end after the simulation or animation I will just add. So, there is a figure. So, where plot t versus e. So, where there are 3 errors. So, in the sense I can actually like take it legends and all. So, I will just use it these things, it is easy for me. So, I am just copying it, but you can type it yourself. So, now this is x error and this is actually like y error in meter, and this is psi error in radians, and this is actually like I call eta error. Okay. So, now if I actually like run this, what I will get finally after the simulation, or you can say animation, it would be giving the error value. So, we can actually like see that. So, now I am just rerunning, but we can actually like you can say play this particular code in a number of ways and you can do it. But what we have done here is actually like last code, the same code, but without adding this, what we have done is a forward differential kinematics, but here we have done the inverse differential kinematics. So, now you can see that there is a very small error. If I actually like see the magnitude, it is actually like in the millimeter level, where the psi e also like you can see that it is 0, whereas you can see x position and y position error is actually like very small. It is actually like open loop. Now, one situation I am actually like adding it just for your benefit. You see that I am actually like giving a situation where the initial condition is actually like different from what you have given a desired value. So, for example, earlier what we have seen, the desired when you put t equal to 0, it starts from 0 and 0, right. X desired and y desired is 0, but now the initial condition I changed is 0.5 meter and 0.5 meter. So, now you can see that the code is completely different, right. So, what that means? So, you have error. Further, I am assuming that this is actually like rotated pi by 4. So, I am just showing it. So, instead of vehicle is actually like 0 position, it is actually like inclined in a 45 degree. Now, you can see that the circle would be with respect to the 45 degree and with respect to you can say the starting point. That is why I said it is a open loop. So, that is what the whole idea of actually like talking about this particular you can say inverse differential kinematics. The inverse differential kinematics is actually like open loop control, not closed loop control. That is what the intention of bringing this inverse differential kinematics into this particular kinematic simulation code. Now, you can see right earlier it was different, but now it is actually like totally different. So, and the error also like you have given actually like starting from supposed to be from 0, but it is starting from 0.5, right, and similarly this is actually like starting from minus 45 degree as the error. So, now you got it clarity. So, you have seen like lecture 5 how to do the kinematic simulation, but in lecture 6 what we have seen, this is the lecture 6, what we have seen is actually like the motion animation along with the forward and inverse differential kinematics. In the sense what one can see, if you bring the vehicle configuration along with wheel, you can definitely add this particular code and then you can make it. So, in the sense the next lecture what we are trying to see, so how to bring that you can say wheel configuration into the vehicle. So, for that we are trying to bring the generalized wheel kinematic model. So, that is what we are going to see in lecture 7, and then we will move forward, and end of that particular week we would be doing the motion animation along with wheel configuration. Even there we will do a kinematic control also, then you can see that more close to the real time, that is what we are interested. So, with that the lecture 6 you can say the kinematic simulation along with motion animation is done, and we will meet on lecture 7 and see you then. Bye.